All right, I'm going to get started here. So if everybody could quiet down, we can get moving. So today's lecture is going to be titled The Neural Network Zoo. This is not my title, by the way. So I just saw a blog post about a bunch of different neural network architectures. I thought it was a really cool title, and I thought it was a really cool idea to kind of go over a bunch of different neural network architectures based off of the same stuff I was teaching you guys for the past 3-4 lectures. I guess this is the 4th lecture and the final one on neural networks. And I thought it'd be cool if I went over how these relate to a bunch of different applications and these architectures that, potentially could yield some more applications by you guys. So, yeah. Of course, I need to acknowledge where I got this name from. So there's this link in the slideshow. I'll also be posting it in a Piazza post with what the neural network zoo really is. It's just like a chart with a bunch of different neural network architectures, ranging from like recurrent neural networks, autoencoders, plus like other stuff like discrete, convolutional, IGN. I don't know what the rest of that stands for, but there's like a bunch of cool stuff on there. A lot of it that's kind of like come in and out of popularity, but they all definitely have validity in at least tackling some kind of problem. They at least do some kind of task really well. And so also, all of the notebooks that I'll be displaying here are from a repository that's on my personal repo, on my personal GitHub page. It's, again, it's listed here. I will be putting this into the Piazza post that I compile with everything on it. So you're welcome to go check that out and run all of the notebooks yourself. However, I should also note that all the stuff I will be running will be using an Amazon instance with a GPU, because the neural network architectures that I'm proposing here, that I'm showing to you guys here, are really computationally expensive. And I realized creating this type of Amazon instance is also kind of a troubling topic. I know that in my first experience with making an AWS instance, even though we gave you that like intro a few weeks ago, it still probably isn't enough to like still get confident and make sure that you're doing everything correctly. So what I'll be doing, hopefully within the next week, is release a video that shows how I start up an instance so that I can use Jupyter Notebooks with this instance. Because there is like an extra caveat that we did not cover during our lecture on AWS. So as a note, I am using the p2.xlarge instance. It's basically just like, it just has like the best GPU on the market. So it's really great for doing this kind of stuff. And it's like relatively cheap if you do it the right way. I think I'm paying like 20 cents an hour or something like that, which compared to other GPU instances, which could be up to like 70, 80 cents an hour, this works out pretty well. Cool. Oh, I guess that's the same thing. All right. So as we kind of continue along the neural network zoo, you'll probably see some familiar faces. So the one on the left is the perceptron model. Basically, the first thing that I introduced to you guys when I was talking about neural networks. Very simple. You have just like a set of inputs, and then a single output. Sum them all together, multiply each element by a weight, and then output a value based off of the step function. Then you have the feed-forward network, fully connected. Again, similar idea, just built off of the perceptron thing, but now we add an activation function instead of a stepwise function. And we're able to add more than just one output. And we can add arbitrarily any number of layers at this point. So yeah, you should be like well drilled with these at this point. I've definitely mentioned them every single lecture. But what may be a little bit more new to you, because I only introduced it last Wednesday, was the convolutional neural network. So this diagram right here is kind of a little bit confusing. It's a little bit different from the like layer-wise representation I showed you before. But again, this is keeping true to like what the neural network zoo proposed and all their different architectures and their like labeling of everything. So you can think of these pink nodes right here as if they're representing the different filters of the convolutional neural network. Basically, this is part of the layers, the convolutional layers. They're just the little subpieces there. And then we output to our dense network right here, which you might recall from this image that they're pretty much the regular neurons in our network. And yeah, basically, that's all the stuff that you should at least know to some degree. But now, there's a little bit of, there are a few other architectures that are a little bit less familiar. So I've at least mentioned what recurrent neural networks are, but you may not really understand what is going on within them because it's like hard to really get an intuition of what's happening. However, you can really think about it as if we basically add loops to our neural network graph. So whereas the feed forward and the convolutional neural network algorithms basically require you to feed down a single pathway when you're basically making a prediction, and then you want to do backpropagation this way. The recurrent neural network adds an element of what is basically recurrence through these loops here, and then now you have to deal with kind of time dependencies as well, or what is probably a little bit more general, like a sequence dependence. So these neural networks, because of this extra loop, are really good at understanding time series data as well as like sequence data. This like extra loop gives the network like a state, and so you can imagine that'd be pretty important for parsing things like language. And if somebody's talking, you want to know, oh, you're talking about the color red versus like reading something. Maybe that could be something like that. Or generating context based off of like what kind of emotions may be going on inside of a sentence. So maybe if somebody says that their day was terrible and that they're upset that their like coffee was spilled or something like that, you want to make sure that you understand that they're upset beforehand, because that this is like generating their bad day. So that's where the recurrence comes in. It can actually store this value in its like higher order representation in the weights. So that pretty much describes the recurrent neural network. What the LSTM, the long short-term memory network, and the gated recurrent unit network are, they're basically just modifications of the same idea, but then they add a little bit of like extra weights inside of here. So it'd be more proper to say that the LSTM and the GRU units, the gated recurrent unit, are both kind of cousins to each other. So they both encompass this like idea of extra layers inside of them, and that give it this like extra power to understand these sequences that recurrent neural networks are somewhat lacking in. Now, this is a very high-level understanding of what's going on, like a very, very high-level understanding of what's going on. And so I really recommend that you check out these two blog posts right here, because they're like extremely useful in understanding first, how RNNs learn anything, and then two, how LSTMs like provide the strength that you need to actually tackle a lot of different kind of problems. So again, these are by two prominent bloggers that I've actually listed before in this class, so Karpathy and Kola, and I really like their explanations. They're very clear to understand, and they've definitely helped me understand what goes on inside of these neural network architectures. And I've also listed two links to two other things related to recurrent neural networks. So one of them is a short film that actually had its script generated by an LSTM. You may have seen this sometime in the past year when they released it, because it's absolutely nonsense, but you can kind of see where it's going. So what they basically did, they fed these LSTM a huge database of movie scripts, things specifically sci-fi movie scripts. And so what they basically tasked it with doing is just generate a new one. So what it would do, it'd create like these characters from this like jumbled memory that it's created inside of its network. And it would basically spit out a screenplay, and then they just acted it out. It's really funny because the actors are pretty good. They're like really good at enacting it, but you don't know what they're saying for the most part, and you can kind of get an idea of like what the recurrent neural network actually understands, and how it's maybe not exactly like what language is modeling, or how it models language, or maybe like how a movie script could model language, but maybe if you added some extra like engineering principles to it, you could actually get it to properly output something that makes sense. Let me see. So also, maybe I'm going to pull this up right now, of the screenwriter, the AI screenwriter called Benjamin, and they this one idea for a feature film that they've generated from this model is really funny. So, set in 1942 in the post-apocalyptic world, the film follows the journey of a young man who falls in love with a sexy couple who have started to fall in love. As they fall in love, they learn that they are not alone in their own way. The film follows the two groups of people who reconnect with the world and their relationship and the secrets they live. It's a great movie. It's coming out soon. So as you can see, like, it's kind of nonsense, but at least the sentences make sense. So that's pretty cool, considering that they basically just feed it character information. They don't give it anything more than just like a sequence of characters. Basically, you could imagine like a database. I think this is probably from like the IMDb like movie synopsis database, and they would just feed in that to them, and it would be able to create something similar to this. And it seems like it has like a nice structure too. So it's clearly able to learn these kinds of like higher order representations of data. And so I've actually I've included in the Neural Network Zoo repository that I linked to earlier an example of an LSTM training on different writings. So I ran this a little bit beforehand because I wanted it to get some kind of like reasonable results before I came to class, and it also took me maybe like 30 minutes to generate most of these results, and even it didn't even actually finish all the iterations that it had planned in the document. But basically, we take I actually realized I can't say his name. Nietzsche. Yeah, so we take Nietzsche's writings, and we basically feed it into our LSTM model. By the way, this is all coded in Keras, so you'll be at least like somewhat familiar. So we add it into an LSTM model, as noted by this layer right here. We feed it in, I think, 128 characters at a time, if I'm not mistaken. And then we use that result, we pass it to just basically a feed-forward model, and then that outputs some kind of classification. And so what this can do is it can output like a probability distribution of possible next characters that will come out, and we can use this to generate whole sentences. So in this loop right here, you basically start the you start the training steps. So you have this model.fit right here. It runs through a single epoch, and that's because the original writer of the script, they basically wanted to make sure that you could see the progress as each epoch proceeds. And then what they'll do is they'll have this variable right here. It's called diversity, and more explicitly, it's probably like the probability that you'll get new stuff, or you could consider it like the randomness of the probability distribution you'll pull up. And so I've ran it for, I think, 20 iterations. At the very beginning, you see this this result right here. So they give it a seed of every nation given themselves. They'll feed that into the RNN, and then they'll be like, okay, what comes next? They'll ask it the question of what character must follow this, and then they'll continually do that until they've generated, I think, 400 characters. So in the first 100 characters, it's the original input. So of every nation given themselves, not even the conscious of the most, and has the conscious of the pre's, and it just kind of falls apart right there. So you can kind of see where it's going, and I think in the lower diversity, what will happen is you'll end up repeating the same sequence over and over again. I think this is pretty apparent in somewhere around here. Maybe if I go a little lower. It does? Oh, are you looking at it right now?
It's like and the conscience of any and the conscience, as opposed to and the conscience.
Yeah.
And the conscience.
So you see, it's just kind of spinning around in circles, really. But when you get to the diversity of 0.5, there's a little bit more coherence in what's happening, and it's still not quite understanding it because I don't think I ran it for enough epochs, but I bet if I ran it for the entire 60 epochs, I could probably expect that the results would start forming pretty coherent sentences, start using proper capitalization, and probably put periods somewhere in the paragraphs. Now, when we crank up the randomness variable, so with the results at diversity 1.2, you'll start seeing just complete gibberish. So maybe some words will appear, but for the most part, it'll just be small sentences that'll cut out here and there. So it's this is pretty late into the iteration step. So it's 11, epoch 11 or so. So we kind of get something going on, PLA into the position of being obliged. Oh, okay, that's why it's so coherent. This is literally the sampled part. So once we get past the sampled part, we have the of people of obliged hard last power, nor of two finds, and just stops being English at that point. But you can see that it's kind of experimenting with some punctuation marks at this point. So at least it's kind of making progress. Let me see what the later results look like before I stopped it. And at about diversity 1.0 here, we may see with this exclamation mine or all the long, however, thus have been to fall, and suffering and grows to me, that when in a vices that belong, while a bad outneeds in the special. So I'd like to argue that even though this is still gibberish, that it's still it's at least using punctuation a little bit more, which is what we'd hope from a model that was just fed in raw data. And again, this probably just needs more iterations to get somewhere pretty good. Now, with the recurrent models, there are some problems. It's very slow to train because instead of being able to use like a bunch of different matrix operations one after another, you're basically dealing with a single matrix operation, and you're kind of restricted to like a relatively shallow network that you must run to actually do all these iterations. And you also have to do this element of going back propagating through time. So you kind of lose complexity, but then you also increase the extent of the problem because you now have to deal with this time element, which adds like a certain large amount of dimensionality to the problem that you're dealing with. All right. Okay. So the next class of neural networks that I want to talk about are called autoencoders. So I think these are extremely interesting. However, the application of them has not been fully explored or may not properly exist. But the idea behind them I still think is pretty intriguing and has had at least some success in the past. So one of the coolest things that these are able to do is the coolness of these nodes, of these autoencoders is that basically you're taking in the input right here and you're calculating you're basically making a loss function that maps it to itself. So effectively you're learning like an identity function through this neural network. And you may think like, oh, why would we ever want to learn an identity function? Why would we want our output to match our input? It just doesn't seem like a good task at hand. But the cool thing is in actually breaking apart these neural networks. Basically, taking the learned representation of the weights and just kind of separating them out. So what you'll notice here in this structure is that there's this kind of bottleneck. There's basically these two neurons that these four-dimensional inputs must go through to actually learn an identity function. What this really gives us is a way to actually compress our data. Basically, we can learn a way to compress the data set that we're given such that it can actually be in a much smaller dimensionality at this point. So clearly there's a lot of possible different areas where you could actually use this autoencoder paradigm. One of the more relevant, or one of the most commonly used one is for embedding into like a space. So let's say you have a really high dimensional data set like MNIST per se, and you want to see how it looks if you put it into like a two-dimensional plane. You basically want a representation where you have maybe a cloud of 9s over here, a cloud of like 3s over here, and maybe because 9s kind of looks similar to 6s, you hope that the 6s are near here, and then 1s and 7s and so on. So you basically would like to represent them based off of these like higher order features, and you'd like to put them near each other so that you can actually like cluster them nicely. So now that's pretty hard to do if you just use like a PCA and stuff like that. You don't really have this extra dimensionality of understanding. Oh, sorry about that. So you don't really understand So the PCA technique, although it does give you a way to reduce the dimensionality of your data, it doesn't really have an understanding of what the data is. And so what autoencoders give us is a way to understand what's the like higher order properties of the data and then better use those to compress the data. And that way we can better form these like clouds of different possible categories in this data. And so it's basically by learning through this bottleneck. Now, this example only shows 3 different layers. However, we can actually extend it to an arbitrary number of layers as well, and then just use those as our encoders and decoders. So to actually get the encoding and the decoding process, what you would do is you learn this identity function. So you just run standard back propagation using the identity, basically training for an identity function. And then you'll basically lop off, if you want an encoder part, you lop off this ending part, basically anything that comes after the bottleneck. And then the representation in the lower dimensions is going to be represented by the output of these 2 neurons now. That acts as your output. Now, if you wanted to take this encoded values and turn them back into decoded values, basically, let's say some kind of lower dimensional representation of MNIST, and you want them back into like their MNIST digits, what you do is just lop off the beginning part right here. Remove the input, and then just use this as your input. Use this bottleneck as your input. So it's just like removing layers. That's pretty much it. Now these other types are basically for doing a few different types of operations. So the variational autoencoder, I think, better like picks up this embedding kind of paradigm that autoencoders are going for. So it's I think it has like an extra value of an extra dimension, I guess, of just, or an extra degree of freedom to really learn these representations. I can't really tell you too much about them, but the good thing is that this link right here has a guide to actually building an autoencoder in Keras that goes over the variational autoencoders. And so you can get a deep dive into that. And then there's the denoising autoencoders. And so what these are great for is actually figuring out a mapping between like a noisy data input, and what the data should actually look like. So the example, again, that is gone over in this page right here is the MNIST data set again, but they just basically add noise to the inputs. And so what they're able to do is they're able to map like like say somebody draws a 7 on like a very dirty desk or something like that. What you want to be able to do is like determine that is a 7 despite all these specs being around there. And so that's how you can use it to do a denoising autoencoder. Is you basically like add extra noise to the input when you're training it, and then it will be able to determine how the noisy input should map to the like non-noisy input. Yeah. Okay. And so the last structure that I really want to talk about during this lecture are called generative adversarial networks. So I did mention these a while back when I was doing, I think, the KNN section. But the basic idea is that you have two different neural network models. Both of them are probably going to be convolutional neural networks because that typically works. And the most common application of the generative adversarial networks have been in like learning representations of images. But the basic idea, what has made these really, really powerful in the things that they have been able to do, is that you take these two networks, you take a generator network, and you take a discriminator network. And so what happens is you train your generator and discriminator against each other. You can think of it as like a game of cat and mouse. The generator tries to create images. Let's just restrict ourselves to an image data set. They try to create images that look realistic. And then what will happen is during the training step, we will use this generated image, we'll mix them in with true images of the data set, and we'll tell the discriminator, okay, tell us which one are fake and which one are real. And so through this paradigm, you basically create a way to understand what data points have been like fudged and everything like that. So the discriminator learns, and then the generator learns how to better fudge these images. So by playing this game of cat and mouse, they increasingly get better and better against each other. And eventually you'll get a generator network that can create things like full human faces when they're basically just missing the entire face. They're a little creepy looking. I'll give you some examples a little bit later. But they're still really interesting that they can actually create this kind of paradigm. And it's mostly it's a very like it's a process that you don't really need to interact with that much. You basically can just let the generative adversarial network learn this representation, just give it a huge data set, and it's a quickly approaching unsupervised learning. However, there still is like an element of what's of supervised learning inside of it, and so it still has to depend on traditional backpropagation and everything like that. But it's still a very, very, very useful algorithm, and it's definitely received a lot of attention in the past 3 years or so. Adversarial network can actually produce. So this is specifically for the MNIST dataset again, and I found the script that would basically let you generate digits this way under this paradigm. And so here's just a display of like I think 128 different MNIST digits. So they look pretty normal. Maybe there's a few weird ones. Maybe this one's a little weird, but we're not really trying to classify the digits. Instead, we're trying to generate these digits from our generator model. So as in cross-form, you create your model, you add you add layers into your model, and this right here is your generator. It's a little bit different from stuff we've seen before in that not only does it have like typical convolution stuff, it'll actually have these upsampling here, and that's because we're mapping from a noisy input that's like a 100-dimensional vector or something like that, and we're outputting a full 128 or 28 by 28 image. So I should also note that I didn't mention it before. You basically, what the generator network does, it just takes in noise. That's how it uses its that's how it's able to generate these images, because that's from the traditional convolutional neural network paradigm. It's basically just taking in noise that you feed into it, and it maps it to some kind of image that it kind of looks like, I guess. But you can actually, you don't need to use noise, and you can actually use inputs that are potentially anything. So the data set that I'll show you in a second is one where they basically take in pictures of celebrities' faces. They put a block on, like they put like a square over their like main part of their face, and then they'll ask the generative network to actually determine what their face should look like. But on this topic right here, you can see the results after the first epoch, and it's kind of cool, I think. Even they may just look like scrawls to you, but you can see that the network is trying to produce something that makes sense. So maybe there's like a 3 here, but there's still like these weird kind of squiggles here and everything like that. But you can kind of see it's maybe like a child just like kind of scribbling around. Now on the second epoch is when you start seeing a lot of emerging results here. So maybe 8s are a little bit more clear, 7s come out, and all these other numbers here. But again, we're still kind of victim to these scribbles here, this, and something like this. Like, could this be an 8 or a 0? Who knows? And as you'd expect, with more iterations, they get even slightly better. I think this one has mostly like readable numbers, with the exception of maybe like I don't know, like 20% of them or so. But that's getting pretty good. And then I think after I didn't even realize that. I forgot that these are separated. So this is actually after the 5th epoch. This is the 10th epoch. And then this is after the 15th epoch. And so as you can see here, this one's doing really, really well. And then after the 20th epoch, we basically have almost entirely handwritten digits. Now, you can conceivably see this work with pretty much any field of images. So I wanna see if I can find that celebrity face. See that face. I think this is what I'm thinking of. Oh, yeah. So they basically gave it a data set that was just blocks covering these images. And so as you can see, they make like a pretty good effort to try to fill in the gaps here. Now they look a little creepy, like this guy's mouth is like really small when you see it again. And at the beginning they look like really far off from from matching skin tone. But it actually makes an effort to create something that's pretty reasonable there. And one of the things they actually end up doing, I'm not sure if it's in this one as well, is they'll be able to take they'll actually take like pixelated versions of these images, and oh wait, actually, hold up, DC again. Yeah, I'm just gonna see if I can find this. I'm pretty sure I remember where I saw these. Oh no, just kidding. So, by the way, this is a blog post I will be linking to on Piazza, but the basic idea for this model that I'm thinking of is they were able to take like pixelated images of celebrities, and they actually got the generative adversarial network to actually determine what those faces should look like from just those pixelated images. And so they look pretty freaky, honestly. But you can see where it's going, and it seems like with hopefully a few tweaks of the algorithm and some kind of extra steps, that will be devised in the future, we could probably create like pretty realistic renderings of what people's faces look like. And they've been actually able to use this technique to create like CSI type zoom in animations and stuff like that. So if you remember, if you've ever watched CSI before, there's this like unrealistic scene where they'll basically say, they'll basically be looking at an image and they'll zoom in and it's really pixelated. And they'll just say like, oh yeah, enhance the image. And then suddenly it just works together. It just fits itself together. They figure out what's there and then it's like, oh, that information has been there all along. They find a key clue to their mystery. See, like realistically with DC GANs, with these generative adversarial networks, you won't be figuring anything out like that. But you can at least get a better idea of what should be there. So let me see, generative adversarial networks enhance CSI. Let's see. Oh, okay, yeah, actually this is the blog post I was looking for. So what you can see here is kind of the evolution of how the DC GAN actually takes apart the image. So right here is the original image. Here's the pixelated version. And you can see what the generative adversarial network tries to infer from the stored database it has. So right here, we get some pretty good results. Like this face looks pretty close to this face. Of course, there's some discrepancies, like a little bit of blurring here and there. And you can start seeing that it'll actually interpret people's eyes a little bit differently, especially when they're blurred. So right here, his eyes look a little bit sneaky. This one is like he's planning some master ploy. And then, so let me see if there's some other good ones right here. And then this one, you can see that it hallucinates these weird wavy images behind this guy. So maybe they just saw a lot of hairs in the data set that they received when they were training it. So it starts to hallucinate a little bit of like a hairy structure here, like he has hair hanging over him or something like that. But yeah, it seems to do a pretty good job for the most part. You get some freaky faces like this, but it mostly works. So let me see about that. So yeah, basically they just take an input image like this and they're able to map it to a like properly looking face. Let me see if I can pull up another example real quick. GitHub. So there's another thing you're able to do with generative adversarial networks. No, that's not it. Is do this kind of operation where you're like basically able to do addition across people's faces. So one of the more interesting things is the thing like where they're able to basically take like the expression of a woman and remove that, like basically figure out what that higher order expression is. Then they're able to take a picture of a man and they're able to make him smiling in kind of a freaky fashion. But like, even though it's not quite there, you can kind of see that it's approaching something that would be really, really cool to do. And so I think one of the more striking images here is the removal or the addition of glasses onto a woman with glasses, which I thought was really cool. You can see all these different generated images of glasses, which are known to be like unique images. So you may think that it's basically just pulling out images from its database of trained images. So maybe it has like a recollection of what a face looks like. Maybe this is like somebody in the database or something like that. But in reality, what's happening is it's actually just generating these novelly. Like you can see this based off of the calculated distance between these generated images and the input images. And you can also notice that this woman's the other properties as well, like her dark hair and everything like that, probably originated from this original picture right here. So this subtraction right here probably encoded that value in there as well. And also they're able to do these things with rotations. So again, it's kind of freaky, but as before, you're able to basically exploit this property of the generative adversarial network to make like these otherwise unheard of transformations of an image. And some more faces. And I thought something that was really cool that came out of this project was album cover generation. So as you can see here, they're basically just like aliens, alien album covers. Like this is some completely different language, and it doesn't really encode key things like that. But it still makes things that look pretty impressive, and I thought were at least like artistically pretty interesting. Does anybody have any questions about things I've covered? Yeah, so clearly the field of research right now is really awesome. There's a lot of cool stuff coming out. Like this has definitely changed my perspective on academia and everything like that, because I definitely want to get involved in more stuff like this. And I'd really encourage you guys to really review the resources that I've provided, primarily out of your own interest. If you think that anything that I've shown you guys was really cool, because this is like a very emerging field right now. It's kind of, I've heard it being called the Wild West from many different people. It's an opportunity to get involved in what is probably going to be a pivotal time in our in our interfacing with computers and everything like that. We're probably going to see a lot more results through neural networks that emulate how the brain operates and everything like that. And I definitely think it's the time to get in on this. So, yeah. Cool. One more thing. There's this thing called wavenet that DMind came out with. I just want to see if I can pull it up. So they basically use this convolutional neural network paradigm, similar to the stuff I was showing you guys before, but instead of applying it to images, they apply it to audio waveforms. And so they're able to use a structure kind of like this. They're called dilated convolutions. So I won't really dive into that. But they're able to create some really, really interesting text-to-speech things. So hopefully, maybe I can get this to play properly. Create text-to-speech examples. So they're able to say this sentence pretty coherently.
1980 American romance and adventure film directed by Randall Kleiser.
So you can hear that it has like a really pretty good understanding of what inflections would sound like, and you can compare that to what the state of the art is before
The
wavenet.
Blue Lagoon is a 1980 American romance and adventure
It's a little bit more
film directed by
jumpy.
Randall Kleiser.
It's really hard to really understand what it's really hard to understand its like tones in the language, and then even like a
Aspects
further
of the
state of an art.
sublime in English poetry and painting, 1770 to 1850.
Now clearly this parametric's a little bit better, but if we listen to the wavenet version again,
Aspects of the sublime in English poetry and painting, 1770 to 1850.
it's definitely a lot better. Yeah, but I think the even cooler part about this is the fact that they actually ran this same kind of model, but instead of mapping it to like a text sequence, they just kind of let it go on its own. So they just fed in a bunch of speech, and the results are really, really cool. So this is not a language. You're not going to be able to understand this. But if you listen to like how the person speaks, how the wavenet speaks, basically, I'll play it again. It has all the proper like mouth movements. It captures like how they breathe and everything like that. And it could be pretty convincing as like a completely different language, as if somebody's just speaking to you in an alien language. So I can play another one.
There's lot o arcade betalen bod yn ein gyda Jeffrey. That's the not back here with him.
We zullen het signal afspreken, zoals het zichzelf is. Yeah, as the hedging we're going to, this was a pack.
Like that sounds like a pretty riveting story if we could understand it. But so, yeah, I think for the most part that's pretty much all I had planned for today. So if you have any questions, I will be hosting office hours Wednesday. You can come see me, and we can just talk about some neural network stuff. So, yeah. Cool. Thanks, guys.